So in this lecture, we're going to talk about addition and subtraction of radical expressions. So let's start out with a basic example here. So 6 root 3 minus 5 root 3. So the idea here is kind of similar to when we combined polynomials and algebraic expressions as like terms. So here, do you see that we have two terms that have a root 3 in them? So the way that we combine them is we just combine them as if these are the coefficients. So if I have 6 root 3's and I subtract 5 root 3's, then, okay, well, you could write this as 6 minus 5 root 3, which would just be 1 root 3. So that's 1 root 3, which is root 3. Of course, you could jump from this to this just by saying I have 6 root 3's minus 5 root 3, so I have 1 root 3, which is this. But here's the, sort of using the math to say that. You're either thinking of this as subtracting the coefficients, or you could think of it also as factoring that out. Okay, but so there's many ways to think about it, but you'd get the same answer no matter which choice you made. So how about these two? Well, now I have 6 times the 4th root of 2 plus 9 times the 4th root of 2, and so those are both the same radicals. So we can just combine the coefficients together. So this would be 6 plus 9. Excuse me, and for the 4th root of 2. And then those coefficients just combine to give us 15 4th root of 2. Okay, how about this here? Okay, so now we have root 8 minus root 32 minus root 18. So those are not, in the current form, have the same radicals involved. So we have to do a little bit of simplification. So what we should do in this situation is simplify those things as much as we can, simplify the radicals as we have been doing before, and then we should be able to combine them. So how can we simplify root 8? So we want to be able to we want to factor these things so that we have perfect squares. And 8 can be written as the square root of 4 times 2. 32 can be written as 16 times 2. And this is already giving us a good pattern because, look, we have a perfect square times a 2. So we're going to end up with a root 2 and a root 2 here. So it's probably good to see if I could get a root 2 out of this. So if I divide this by 2, then I get 9. And that is also a perfect square. Okay. If you don't see that pattern immediately, we should still remember that you need to factor it so you have perfect squares. Okay, so then this becomes what? Well, that's square root of 4, square root of 2, minus square root of 16, square root of 2, minus square root of 9, square root of 2, just using that multiplicative property that we had before. This is 2 root 2, this is 4 root 2, and then this is 3 root 2. And then combining all those things together, we will have 2 minus 4 minus 3 root 2, just combining the coefficients together. So 2 minus 2 is negative 2, minus 2 is negative 5. So this would be negative 5 root 2. Okay, so next example, very similar. Let's see if we can simplify these roots first. So 48, we could write this as 16 times 3, right? 16 times 2 is 32 plus 16. And then 3 times 9 times 3, and then 2 root 25 times 3. And that's looking promising because we had a factor of 3 in each of these, and the other factor is a perfect square. So we'll have root 16 root 3 minus 3 root 9 root 3 plus 2 root 25 root 3. So this is 4 root 3 minus 3 times 3 root 3 plus 2 times 5 root 3. And so that's 4 root 3 minus 9 root 3 plus 10 root 3. And you know what? We could just combine those. So 4 minus 9 is minus 5 plus 10 is positive 5. So 5 root 3. Okay, so for our next example, we're going to be simplifying some things that have some variables, right? Variable x. But in this series of problems, assume any variables under an even root are non-negative. So what that just means is, you know how we had that property before that says, if you recall, that the square root of x squared is equal to absolute value of x, right? But if x is non-negative, i.e., in other words, if x is greater than or equal to 0, then this, if x is already greater than or equal to 0, then when you take the absolute value, that's going to be the same as x, okay? You're not going to have to negate it. So what we're just saying here is that if you do get absolute values, which we would, you could just forget them. Okay, so what would this actually be equal to? So this would be 2 root 50 root x squared minus 8x root 18 minus 3 root 72 root x squared. Okay, so what do we have so far? So we have 2, and then this we could factor a little bit more, right? 50 is 25 times 2, and then the x squared becomes just an x, right? Now, it would be absolute value of x, but we're assuming up above that we said that it's non-negative, so we could just make that an x. This is 8x, and then 18 we could do 9 times 2. And then 72, could we do anything for that? So if we divide that by 2, what do we get? Sorry. So we get 36, right? So 36 times 2, and 36 is a perfect square, right? Square root of x squared, we'll just make that an x again. And keep simplifying. We have 2 root 25, root 2, and an x. You know what? This x, let's bring the x over here. It's standard to kind of put all this stuff that doesn't have a root anymore in front of all the radicals. And then we'll have 8x root 9 root 2, and then minus 3x root 36 root 2. Okay, simplifying some more. Now this is a 5 root 2. Then we have 8x times 3 root 2, and then 3x times 6 root 2. Okay, can we get any more simplified? So this would be 2 times 5 is 10, so 10x root 2 minus 8 times 3, 24x root 2, and then minus 18x root 2. All right, and so these are like your coefficients again, right? They're all in front of the same root, so then we can do the subtraction, right? So 10 minus 24 is minus 14, right? And then minus 18, we'd have what? Minus 32, is that right? Okay, now let's look at this example here. Okay, so what can we do? So 9a, and then we can break these up. Root 20, root a cubed, root b squared, plus 7b, root 45, root a to the 5th. Okay, so the odd ones, we're going to have to break those up so we have a perfect square. So this is 9a. Can we get a perfect square out of 20? Well, we could do 4, right? So 4 times 5. And then this, we could write that as a squared times a, and b squared will just give us a b when we take the square root. 7b, 45. Can we do anything with with this? 45 is 9 times 5, right? And a to the 5th, we'll have to write that as a to the 4th times a, right? Okay, so then we'll have 9a, and then root 4, root 5, root a squared, root a, and then that b, you know what, we can bring that b over here, right in the front. Okay, and then we'll have 7b b, root 9, root 5, root a to the 4, root a. You know, a lot of these steps, you're going to get used to them, and you can kind of skip them. So this root 20, you probably could actually just jump right to this, okay? Or when you write it as 4 times 5, you could immediately write that as 2 root 5, which is what we're going to get in this next step here. So we'll have 9ab, 2 root 5, and then square root of a squared is a, and square root of a we'll leave alone, and 7b times 3 root 5, a to the 4th. When you take the square root of that, it'll be a to the 4 over 2, right? A to the 4 divided by 2, so that's just a squared. Or the other way is a squared times a squared is a to the 4, so that's why that's the square root. And we're getting closer. We have, okay, 9a squared. So 9 times 2 is 18. And then a squared, we have 2 on the outside, and then a b. And then we have root 5 root a. So let's just write that as root 5a. And then we have 7 times 3 is 21. A squared b. And then root 5a. And then look at this. We actually have two terms that have the same things with the variables involved and the same roots. So you see, we could combine the coefficients like we did before. 18a squared b plus 21a squared b. You see that everything under the lines here, they're actually the same. So we actually only have to combine these coefficients. So what would we get? 39 a squared b root 5a.